Networks can also be complex. Networks have a structure, but it can often be a complex structure. So we've been looking at big data as a network. And we'll do this quite often, represent big data as a network. Let's look at the concept of the order of a graph. That's the number of vertices. These are small order networks, and of course, big data typically has high order. We'll also define a concept of adjacency. Two vertices are adjacent if they're connected by an edge. We'll denote it by the tilde there. So V1 is adjacent to V2, so we write it like that. V3 is not adjacent to V7. Now, graphs with identical adjacencies are essentially the same graph. They're isomorphic. So if I have another structure and I can label the vertices so that I have the same adjacency relationships as the original, then we'll say those are the same graph, or mathematically precisely, they're isomorphic. So here's some simple networks, very low order. Here's a simple network. It's very high order. M and N could both be 10 to the 50th. But this is not a complex network. It's actually just a grid graph. Large, but not complex. These, however, are the kind of networks we look at when we study big data. Large, complex. So how do we distinguish simple networks from complex networks? Well, the underlying structure is what's actually known as the topology of the graph. We're just going to look at one simple idea of topology. So to begin with, if a graph can be drawn on a surface without its edges crossing on that surface, then we'll say the topology of the graph is defined by the topology of that surface. So here's a donut, a torus. It has genus 1. So one hole, a double torus has two holes, and we'll say it has genus 2. And so we'll be using genus to talk about graphs. Let's look at a sphere. It doesn't have any holes, and as a matter of fact, a sphere is essentially the same as the plane. All you have to do is take the infinity in the plane. You know, as you go out the plane in all directions, you reach infinity. Take all that infinity and just call it the North Pole. That's called stereographic projection, i.e. it's just drawing maps. So the line from the North Pole to the plane uniquely associates points on the sphere to points in the plane, and the North Pole therefore has to be infinity. Now a handle on the plane is essentially a handle on a sphere. And if we deform the sphere, then we can deform it into a torus. And notice we deform it in such a way as we don't tear or change the structure, so the number of holes is preserved. And so the genus of a surface is essentially the same as the number of handles that you would have to put on the plane to get that surface. This is, at least is for what are called orientable surfaces. Now the genus of a graph, and then again this is orientable, the genus of a graph is a surface with the lowest genus on which the graph can be drawn without the edges crossing. Planar graphs can be drawn in the plane without any edges crossing. And because of that, they can also be drawn on a sphere, and a sphere has genus 0. So therefore a planar graph has to have genus 0 as well. Essentially this is a theorem. A planar graph has genus 0. Now these are planar graphs. Pretty easy to see that they're planar graphs. We can actually say more about planar graphs because we use what's called the Euler characteristic. The vertices, number of vertices minus the number of edges plus the faces is equal to 2, as long as you include the outside region as one face. So for example, here we have 5 vertices and 7 edges and 4 faces, 4 regions defined by this partition. And notice if we take 5, subtract the 7, add the 4, then we get 2. Now let's do the same thing with this small grid graph. If you count them, we have 15 vertices, actually 5 times 3, and 22 edges. And if you count them, there are 9 faces. 15 minus 22 is a negative 7, plus 9, and that's again equal to 2. So I guess I assume you know calculus and linear algebra, but not arithmetic. Now once again, we take 8 and 12. 8 minus 12 is negative 4, and there are 6 regions. So once again we get 2. So we can actually distinguish planar graphs in a number of different ways. A graph with edges that cross may be isomorphic to or the same shape as a planar graph. So both of these graphs are actually planar. They can be redrawn in the plane without edges crossing. We can actually see this if we embed these on polytopes in three-dimensional space. Now, polytopes are closed surfaces with no holes or handles. So here we have the polytope that we use for this graph, and you can see that that corresponds to that graph. Here we've labeled the blue vertex, and notice the blue vertex is connected to each of the 3 black vertices, and that forms the triangle, the inner spine there. And the red forms an inner spine there in the front, and the green is connected to all 3 of those. And so here is 2 surfaces that have genus 0. And therefore, these graphs have genus 0, and that means that these graphs have to be planar. Now we can redraw the first graph like this. We just take the red dot and we move it outside, and now we have the planar representation of the graph. You can do the same thing for the second graph, and the hint here, what you have to actually do is choose one of the faces to be the outside region, and then it falls right out. Now a torus graph can be drawn on a torus but not on a sphere, and to do this we can draw the graph on a polytope, although it's not exactly a polytope. It's actually a union of polytopes glued together in a certain way. So here's my polytope representation, and here it is in a different form, and clearly you can see it forms a torus. There's a hole, and that means it's genus 1. Every graph can be drawn with no edges crossing on a plane as long as you have enough handles. Complex networks have a structure, but it tends to be a structure with a very high genus. Lots and lots and lots of handles. All of these can be embedded on a plane with handles as long as we put in enough handles. Now just looking at these two, you can see we're going to have a lot of handles. In practice, this theorem is not very useful because finding the genus of a graph is NP complete. Once again, like the subset sum problem, we're looking at 10 to the 50th years. For small graphs, yeah, we can get the genus, but large, no way. But let's suppose we know the genus, or we have some sort of relative feel for what the genus is. If the genus is small, finding a maximum clique tends to be fast. For example, a planar graph cannot have a clique with more than 4 vertices, and a torus graph cannot have a clique with more than 7 vertices. So that means instead of checking all subsets of vertices, you're only checking a very small collection of subsets. Now, what about if the genus of a graph is large? Well, if the genus of a graph is large, then it sort of implies that the vertices have a lot of neighbors on average. We can use this idea. In fact, large genus of a graph is in some ways more useful than high dimensionality of a dataset. It's certainly easier to imagine large genus, i.e. lots of handles on the plane, than it is to think about extremely huge dimensional spaces. So in summary, the 3 V's tell us what? Big data is high volume, high variety, and high velocity. It also says that we need algorithms that can extract information quickly, and we need classifiers that can linearly separate in very high dimensions. Big data is massive and messy, the 3 V's, cursed, but most importantly, big data does have a structure, and it's typically represented by a complex network, and such representations can often lead to useful algorithms and approaches. So even though it may seem that big data is uncontrollably large and uncontrollably messy and complex, in fact, it's often the very structure that makes it complex that allows us to extract information that's very useful.